Today's session is about single variable calculus, polar curves. Here we shall discuss about radius of curvature in Cartesian form, parametric form and polar form, Cartesian form. If y is the function of x and is a Cartesian curve form, then radius of curvature ρ is equal to this, where y1 is equal to dy by dx and y2 is equal to d square y by dx square, that is second order differentiation. Note if y1 is infinity at any point, then radius of curvature ρ is given by this. Approach. Step 1. Find y1 that is dy by dx. Step 2. Find y2 that is d square y by dx square. Step 3. Solve for ρ. Let's understand clearly with help of some examples. Example 1. Find the radius of curvature at the point this, of this curve. Solution, given, this step 1, differentiation of this is y1 is equal to 3x square plus here we are differentiating with respect to x, so y cube will become 3y square dy by dx in 3axy, product rule is applies, first keeping y as constant along with 3a, differentiating x, will be 1 and we get 3ay, plus, now keeping x as constant along with 3a differentiate y we get 3ax dy by dx. Bring dy by dx terms towards left, we get this, bringing this down, dy by dx is this. Radius of curvature at the point 3a by 2, 3a by 2 is asked, so dy by dx at 3a by 3, 3a by is calculated, that is plug in these values for x and t, we get this, simplifying we get y1 is equal to minus 1. Step to find y2 that is d square y by dx square, dy by dx is this, differentiating again, here division hence quotient rule, keeping denominator differentiate numerator. In numerator 3a is constant and differentiation of y is dy by dx minus differentiation of 3x square is 6x. Minus, keep numerator as such and differentiate denominator, 3y square is 6y dy by dx, minus, differentiation of 3ax is 3a, whole divided by denominator square. As ρ at the point 3a by 2, 3a by 2 is required, plug in the values for x and y, we get this, now this and this are same, taking out as common, we get this, minus 12a, minus of minus 12a, minus 24a. This and one of this get cancelled, taking LCM, we get this, simplifying, we get minus 32 by 3a. It cannot be negative, hence take it as positive. Step 3. Solve for ρ. Put the value of y1 and y2. y1 is minus 1 and y2 is 32 by 3a simplifying, we get ρ as 3a by 8 root 2 dot. Example 2. Find the radius of curvature at point A, 0 on this curve. Solution, given this, step 1. Find y1 that is dy by dx, here, xy square, so product rule, first keeping y as constant differentiate x is 1, we get y square, plus, now keeping x as constant and differentiate y square, is to y dy by dx, is equal to a is constant hence differentiating it is 0 and minus x cube become to x square. Rearranging, bring dy by dx to left side and all the other terms to right, we get this. At the point a, 0, is given, put x is equal to a and y is equal to 0, and simplify, we get infinity. We know, if y1 is infinity at any point, then radius of curvature is obtained using this formula. Now again, step 1, find x1 is equal to dx by dy, that is now we shall differentiate with respect to y. Differentiating this, xy square, product rule, first keep y as constant and differentiating x is dx by dy, then keep x as constant, differentiating y square is to y. As constant hence will become 0 and x cube will become 3x square. Bringing dx by dy to left and other terms to right, we get this. At point a dot 0, plug in x is equal to a and y is equal to 0, simplifying, we get x1 is equal to 0. Step 2, find x2. We got dx by dy as this, differentiating it again, here we see division, hence quotient rule. Denominator times differentiation of numerator, minus numerator times differentiation of denominator, whole divided by denominator square. We get this. At the point a dot 0, substituting x is equal to a and y is equal to 0, we get this. Simplifying, we get x2 is equal to minus 2 by 3a. Step 3, solve for rho. Substituting the values of x1 and x2 here, we get this. Radius is positive, hence we take it as 3a by 2. Example 3. If rho is radius of curvature for y is equal to by pluses. Solution. Given y is equal to ax by a plus x, since we need y by x, we shall rewrite this as this, that is bringing x of ax to left hand side, we get this. Step 1, find y1, differentiate y is equal to ax by a plus x, here division, so quotient rule, keep denominator a plus x as such and differentiate numerator ax, which becomes a, as a is constant and differentiation of x is 1, constant multiplication rule. We get a, minus, keep numerator as such and differentiate denominator, a being constant will become 0 and x will be 1, divided by a plus x whole square. Simplifying, we get y1 is equal to a square by a is equal to x whole square. Step 2, find y to dy by dx. We got this. Differentiating again, here division, so quotient rule, a plus x whole square times 0, minus, a square times differentiating of denominator is, expand a plus x whole square and then differentiate, which is a being constant becomes 0 plus 2ax becomes 2a, and x square becomes 2x, whole divided by denominator square, square of a plus x, whole square, that is a plus x whole to the power 4. Simplifying, we get y2 is equal to minus 2a square by a plus x whole cube. Step 3. Solve for rho. Substitute the values of y1 and y2. We get this. We know from given y by x is equal to a by a plus x, substitute y by x for a by a plus x, we get this. Bringing this up, it becomes ax cube by 2y cube. Since in question to rho by a to the power 2 by 3 is asked, so first, we will bring this 2 and a to left hand side, then, multiply to the power 2 by 3, both side, we get this. Here 3 and 3 get cancelled, and here 3 by 2 and 2 by 3 get cancelled, we are left with this. Now, x by y whole square, multiplied by 1 we get this plus x by y whole square multiplied by y to the power 4 by x to the power 4, cancelling y square and x square, we get y by x whole square, hence proved. Radius of curvature parametric form. Rho in parametric form is given by this, where x1 is dx by dt, y1 is dy by dt, x2 is d square x by dt square, and y2 is d square y by dt square. Approach. Step 1, find x1 and x2. Step 2, find y1 and y2. Step 3, solve for rho. Let's understand clearly with an example. Example 4. Find the radius of curvature for the curve x is equal to a cos t, y is equal to a sin t. Solution. Given, x is equal to a cos t, y is equal to a sin t. Step 1. Find x1 is equal to dx by dt and x2 is equal to d square x by dt square. X is equal to a cos t. x1 differentiating a cos t is minus a sin t. x2 differentiating minus a sin t is minus a cos t. Step 2. Find y1 and y2. y1 is equal to differentiating y, a sin t, is a cos t, and y2 is differentiating y1 a cos t, is minus a sin t. Step 3. Solve for rho. Plug in the values of x1, x2, y1 and y2 in this formula. We get this. Take this a square and this one out as common, we get a square to the power 3 by 2. This 2 and this to get cancelled, we get a cube. sine square t plus cos square t whole to the power 3 by 2. This becomes 1 as sine square t plus cos square t is 1. In denominator, minus a sine t times minus a sine t is a square sine square t, minus of minus is plus, a cos t times a cos t is a square cos square t, taking a square common out, sin square t plus cos square t becomes 1, simplifying, we get rho is equal to a. Example 5, find the radius of curvature for this curve. Solution, given x is equal to a log secant t plus tan t and y is equal to a secant t. Step 1, find x1 and x2. X is equal to a log secant t plus tan t. x1, a is constant. Differentiation of log secant t plus tan t is 1 by secant t plus tan t. Differentiating secant t is secant t tan t, plus differentiation of tan t is secant square t. Taking secant t out, tan t plus secant t, this and this get cancelled. We get x1 is equal to a secant t. X2 differentiating a secant t again, we get a secant t, tan t. Step 2, find y1 and y2. Y is a secant t. y1 differentiating a secant t is a secant t tan t. y2 is equal to differentiating y1 a secant t tan t. Here product rule, a is constant, keeping secant t such and differentiating tan t is secant square t plus now keep tan t, and differentiating secant t is secant t tan t. Taking a secant t common out, secant square t plus tan square t is secant square minus 1, and we get y2 as a secant t times to secant square t minus 1. Step 3, solve for rho. Substituting the values od x1, x2, y1 and y2 we get this. Here a square secant square t is common, taking it out, we get 1 plus tan square t is written as sec square t minus 1, whole to the power 3 by 2. In denominator, a secant t and a secant t will become a square secant square t times to secant square t minus 1, minus here, tan square t can be written as secant square t minus 1, so we get a square secant square t times secant square t minus 1. Simplifying we get rho is equal to a secant square t. Radius of curvature, polar form. Radius of curvature of polar form. Let r is equal to f of O be a polar equation of curve. Then, radius of curvature rho is given by this, where r1 is equal to dr by d theta and r2 is d square r by d theta square. Alternate method, radius of curvature in pedal form rho is this. Approach. Step 1, find r1 is equal to dr by d theta. Step 2, find r2 is equal to d square r by d theta square. Step 3, solve for rho. Example 6, find the radius of curvature at any point r is equal to a e to the power m theta. Solution, given, step 1, find r1 r is this. r1 differentiating a e to the power m theta is a m e to the power m theta. This is equal to rm, as r is equal to a e to the power m theta, given. Step 2, find r2, differentiation of a m e to the power m theta, which is a m square e to the power m theta, equal to r m square, as r is equal to a e to the power m theta, given. Step 3, solve for rho. Substitute the value of r1 and r2, simplifying we get rho is equal to a e to the power m theta times root 1 plus m square. Example 7. Find the radius of curvature of the curve r is equal to a sine n theta at pole. Solution, given, r is equal to a sine n theta. Step 1, find r1. r1 is differentiation of a sine n theta, which is a n cos n theta. Step 2, find r2. r2 is differentiation of a cos n theta, which is minus a n square sine n theta. Rho at the pole is required, theta at pole is 0, substituting theta by 0. R is equal to a sine n 0 is equal to 0. R1 is equal to a n cos n 0 is equal to an. R2 is equal to a n to sine n theta is equal to 0. Step 3, solve for rho, plugging the values of r. R1 and R2 we get rho is equal to a n by 2. The radius of curvature at pole is n by 2. Example 8. Find the radius of curvature at the point R. Theta of the curve R is equal to a 1 plus cos theta square by. Solution given. R is equal to a 1 plus cos theta. This can be written as R by a is equal to 1 plus cos theta. Step 1. Find R1 differentiation of a 1 plus cos theta is minus a sin theta. Step 2. Find R2 differentiation of a sin theta is equal to minus a cos theta. Step 3. Solve for rho. This is the formula. Plug in the values of R, R1 and R2. We get this. In numerator, taking a square to the power 3 by 2 common, 2 and to get cancelled, we have a cube. And in denominator a square is common, a cube and a square, cancelling, we get a in the numerator. Expanding 1 plus cos theta whole square, we get this, plus sin square theta, cos square theta plus sin square theta is 1, that is in numerator, a times 2, 1 plus cos theta, whole to the power 3 by 2. In denominator, expanding 1 plus cos theta whole square, we get this, plus, to sin square theta, it can be written as sin square theta and sin square theta, multiplying these two we get cos theta plus cos square theta. Cos square theta plus sin square theta is 1, simplifying, we get this. 2 to the power 3 by 2 can be written as to root 2. Similarly 1 plus cos theta to the power 3 by 2 can be written as 1 plus cos theta, under the root 1 plus cos theta, 1 plus cos theta and 1 plus cos theta get cancelled, 1 plus cos theta is written as to cos square theta by 2, we get this. Simplifying, root 2 times root 2 is 2, this 2 multiplied with this 2 is 4, root of cos square theta by 2 is cos theta by 2 and we get 4 by 3. Cos theta by 2. Rho is this. Squaring both sides, we get this. We know cos square theta by 2 is 1 by 2, 1 plus cos theta. 1 plus cos theta is R by a, given a get cancelled. We get rho square by AR is equal to 8 by 9, which is constant, hence proved.